Permafrost sounds simple, permanently frozen ground. But the reality is more complex and much more important. Permafrost is soil, rock, or underwater sediment that stays at or below 0 degrees Celsius for at least 2 years in a row. In some places it is thin, hiding just below the surface. In others it reaches more than a kilometre deep. The oldest known permafrost has remained frozen for hundreds of thousands of years. That means it is not just cold dirt. It is a frozen record of past environments, packed with ice, minerals, roots, dead plants, and ancient organic material. For most of human history, this frozen ground seemed stable enough to ignore. Now, as the climate warms, it is becoming one of the most important hidden systems on Earth. To understand permafrost, it helps to separate it from the surface layer above it. In many cold regions, the top layer of soil thaws during summer and freezes again during winter. Scientists call this the active layer. Plants grow in it, insects live in it, water moves through it, and seasonal change plays out there every year. Permafrost begins underneath, where the ground stays frozen continuously. This matters because a landscape can look normal on the surface while depending on a frozen foundation below. A road, a house, a forest, or a pipeline may all sit on ground that behaves like solid support only because it is frozen. When warmer summers deepen the active layer, thaw can reach material that has been locked away for centuries or longer. Permafrost is mostly a Northern Hemisphere phenomenon. It underlies around 15% of the Northern Hemisphere and about 11% of Earth's total surface, covering roughly 18 million square kilometers. Huge areas of Siberia, Alaska, northern Canada, Greenland, and Arctic coastal regions contain it. But permafrost is not limited to flat Arctic tundra. It also exists in high mountain regions, including the Tibetan Plateau, where elevation keeps the ground cold enough. In the Southern Hemisphere, it is much rarer and mostly appears in mountain environments such as Patagonia, New Zealand's Southern Alps, and the coldest Antarctic highlands. The key condition is not snow cover or visible ice. It is whether the ground temperature remains frozen long enough for permafrost to form and persist. The reason permafrost matters globally is carbon. Cold northern landscapes have accumulated dead plant material for thousands of years. In warmer soils, microbes break that material down, releasing carbon into the air as carbon dioxide or methane. But when the ground freezes, decomposition slows dramatically. Organic matter that would normally rot can remain preserved, layer after layer, as new vegetation grows above it. Over time, permafrost soils become enormous carbon stores. They are not carbon sinks in the neat, engineered sense. They are messy natural archives created by cold, water, slow growth, and incomplete decay. When these soils thaw, microbes can wake up and begin digesting old material again. Carbon that stayed trapped underground for millennia can start moving back into the atmosphere. What comes out of thawing permafrost depends on the conditions underground. If the thawed soil is relatively dry and oxygen can enter it, microbes tend to produce carbon dioxide. If the ground is waterlogged and oxygen poor, they can produce methane instead. Methane is especially concerning because it traps much more heat than carbon dioxide over shorter periods, even though it does not last as long in the atmosphere. This creates a climate feedback loop. Warming causes permafrost to thaw. Thaw allows ancient organic matter to decompose. Decomposition releases greenhouse gases. Those gases add more warming, which can encourage more thaw. It is not the main cause of climate change, and it does not replace human fossil fuel emissions. But it can make the problem harder to control. One mistake is to imagine permafrost thaw as an instant doomsday switch. Scientists generally do not expect it to trigger sudden runaway warming by itself. The more realistic concern is slower but still serious. Permafrost emissions can become a major additional source of greenhouse gases. Some estimates compare future annual permafrost emissions to global emissions from deforestation, or even to the yearly emissions of large industrial countries. That matters because climate planning depends on carbon budgets. If natural systems begin adding more emissions as the planet warms, humans have less room for error. The difficulty is that permafrost does not thaw evenly. Some areas change gradually, while others collapse abruptly. Some become wet and methane-rich. Others drain and produce more carbon dioxide. The physical collapse of permafrost can be dramatic. Many frozen landscapes contain large amounts of ground ice. While frozen, that ice helps hold soil together and preserves the shape of the land. When it melts, the ground can lose volume, strength, and structure. The surface may sink, crack, slump, or collapse into uneven depressions. In some places, thaw creates thermokarst landscapes, where pits, ponds, unstable slopes, and new lakes appear as ice-rich ground gives way. This is not just a scientific curiosity. It can change drainage patterns, damage ecosystems, and destroy infrastructure. What once behaved like a stable foundation can become saturated, shifting, and unreliable. In cold regions, climate change is not only happening in the atmosphere. It is happening under people's feet. Communities and industries across permafrost regions face a direct engineering problem. Buildings, roads, railways, airstrips, fuel tanks, and pipelines were often designed around the assumption that frozen ground would remain stable. When that assumption fails, structures can tilt, buckle, crack, or become unsafe. Estimates suggest that by 2050, a large share of infrastructure built on permafrost could be at risk. The financial costs may reach tens of billions of dollars in the second half of the century. But the human cost can be even more immediate. In remote northern communities, a damaged road or runway can affect food delivery, medical access, emergency response, and fuel supply. Adapting may require redesigned foundations, ground cooling systems, better monitoring, or relocation from unstable areas. Permafrost thaw also creates pollution risks. Frozen ground can act as a barrier that keeps buried contaminants from spreading. Across northern regions, thousands of sites contain fuel residues, industrial waste, mining byproducts, or other toxic materials. Some were stored in places that once seemed safely frozen. As the ground warms, water can begin moving through areas that were previously sealed by ice. Pollutants may then leak into rivers, wetlands, coastal zones, and local food webs. Natural deposits are another concern. Permafrost regions contain large amounts of mercury accumulated over long periods. If thaw changes water flow and sediment movement, that mercury can become more mobile. For communities that rely on fish, wildlife, and local ecosystems, thawing ground can turn old contamination into a present-day threat. Another fear often connected to permafrost is ancient disease. Frozen ground can preserve biological material for a long time, including microbes. So the idea that thaw might expose old microorganisms is not impossible. However, the risk of permafrost thaw directly causing a major pandemic is generally considered low. For that to happen, a pathogen would need to survive freezing, remain infectious, reach a suitable host, and spread effectively. Those are several difficult barriers. Still, the issue should not be dismissed entirely. Warming can change animal ranges, water quality, human activity, and exposure to disturbed ground. The more realistic health concern is not a movie-style ancient plague, but a wider set of environmental changes that can increase stress on people, animals, and ecosystems. Permafrost is also a hidden regulator of northern landscapes. When ground stays frozen, it can block drainage and help maintain wetlands, shallow lakes, and saturated soils. When it thaws, water can behave in new ways. Some areas become wetter because melting ice creates depressions that fill with water. Other areas become drier because thaw opens pathways for drainage. These changes affect plant communities, wildlife habitat, wildfire risk, and greenhouse gas emissions. Wet, oxygen-poor ground can favor methane production. Drier, oxygen-rich soil can release more carbon dioxide. Vegetation may shift as shrubs expand into tundra, while forests can suffer from unstable roots and changing moisture. The surface world reorganizes when the frozen layer beneath it changes. The bigger lesson is that permafrost is not a remote Arctic detail. It is part of the Earth system, a frozen foundation, a carbon reservoir, an engineering support, and a chemical archive all at once. As warming continues, more of that system becomes active. The most important response is still reducing human greenhouse gas emissions, because less warming means less thaw and fewer feedbacks. But adaptation also matters. Arctic and mountain regions need better ground monitoring, safer construction standards, contamination planning, and respect for local knowledge from communities already living with these changes. Permafrost reminds us that climate change is not only about melting ice caps or rising air temperatures. Sometimes the most consequential changes begin underground, quietly, until the ground itself starts to move. If you found this helpful, please like this video and subscribe for more explainers.